everyone. Welcome to this week's graphics programming virtual meetup. We follow the Berlin Code of Conduct. And we have a Discord server. If you haven't joined, you can join by this link. Or you can ask in the chat and I can put this link in the chat. We also have a Twitter account that you can follow and we will announce our meeting there. And all the past videos are on this YouTube channel just called Graphics Programming Virtual Meetup. And we just finished the Tiny Render series. And today, Jon Baker will talk about his cool softbody simulation program. And afterward, we usually hang out here a little bit to talk about some random graphics related stuff, but you can leave wherever you want. So yeah. So I will hand out to Jon now.
Hello, good evening, everybody. Go ahead and get this up real quick. Okay. Okay, so my name is Jon Baker, and this is my website here. If you're interested in reading any more about this project or any of the other projects I've been working on. This is going to be covering real-time soft body physics, and specifically there are different approaches to this type of simulation, and this is using spring mass damper systems. So if you have a computer science background, you probably are familiar with the data structure of a graph. And I think this is a very appropriate definition for this particular context. It's a structure to represent pairwise relationships between a set of elements. And so that consists of nodes and edges. Nodes are the points on the 3D model which are used to represent the locations and other physical quantities. And so there's a mass, point mass, and it's traveling at some velocity. Edges are the undirected connections between these nodes, and they're sort of the vectors along which the forces are applied. So they conceptually act as both a spring and a damper. In the program here, they're represented as a line drawn between the two ends. So the physics model has four different components. There's Hooke's law, which models the behavior of springs. Then you have proportional damping, which prevents, well, so it damps the behavior of the springs. And then you have Newton's second law, which is applied to each node, basically to take all the forces that are acting on each node and see how that translates into a resulting acceleration on that node. And then, of course, gravity is another of the forces that will be acting upon it. So Hooke's law basically looked at the length of the spring relative to some base length, and that's in the input model. As you'll see, there's some length that is established just by the initial positioning, and so as the length of that edge varies with respect to that base length, a compressed edge is going to apply a force to extend back to the base length. So it's going to try to extend. And correspondingly, if it's stretched, it's going to try to compress back to the base length. So proportional damping, it's a second order force that counteracts motion. So it's applied very similarly, where this counters the displacement. This counters sort of displacement and velocity. So basically, it slows it down. Otherwise, the springs would just be, they're there's no damping, I guess, is the easiest way to describe it. So by keeping, and I'll describe this on a couple of slides later, but basically, it looks at the previous value of the velocity at the that was the value of velocity at the previous update, to remove any sort of sequential dependence when you're evaluating the graph. And like I say, I'll go into that. But this makes multi-threading very easy to do with this type of structure. So Newton's second law, just a basic thing here. So it's the rate of change of momentum is directly proportional to the sum of the forces applied. And so if you know all the forces, then you can determine the differential in momentum. And right, so that ends up, momentum is the mass and velocity, and then you take the derivative, and you've got force equals mass times acceleration. So the way we use that is each update, the acceleration is computed as the summation of all the forces divided by the node's mass. Then you have the next velocity value is updated from an acceleration of this magnitude acting upon the node for the duration of the simulation time step. Then you have the next position is computed as a sum of the old position and a velocity acting upon the node for the duration of that time step. So, or the previous there. So the data for each node consists of two sets of physical quantities, one for the next set and one for the previous. So each update, the previous values are used to compute the next values, and then the old next values become the old values. Right, so this prevents any data race type of conditions, which would create sort of an unpredictable behavior. So anytime that you're looking at the data for the neighbors, that's going to be done with the previous values. So this is cool, but without any sort of excitation, this system just kind of sags, right? Under the force of gravity, it sort of just collapses down on itself. But so basically what I've done is there's some nodes here. I did a car chassis, sort of like. But so here at the wheels are nodes that are flagged as anchored. So by moving those around manually, right, by in this case it's Perlin noise, I'm introducing a displacement, which then via Hooke's law, I'm inducing forces that then propagate outwards to all the neighboring and eventually all the nodes in the graph. So that's kind of a cool little thing. This particular GIF is so basically it's got gravity turned down very low and then suddenly ramping it up to a high value. So you see that sort of a compression there, and red is tension and blue is compression, I think. Anyway, it's showing the displacement from the base length. So as it's longer, it's one color, and as it's shorter, it's another color. So the model I made in Blender, exported in OBJ, and got it that way. For the suspension connections, I went through and just made something that as you hit a key, it would iterate through the thing. Anyway, so just numbered connections there. So it's fast for a model this size. I think there's like maybe a couple hundred points. I want to say 470. I'm not 100% sure about that. But the so it's less than 2 milliseconds each update. The GPU implementation is something that I've been thinking about for a while, but I haven't gotten to. And that's so that would be kind of a almost like a kind of a pointer concept on the GPU. And I've been thinking about ways to do that inside of a like an SSBO. So anyway, this graph kind of idea, I thought about some other applications for that, like circuits is one, and so that's another thing that I've sort of been thinking about. So we'll go ahead and show what I've got here. And if anybody has any questions, I'd be more than happy to share or answer. So basically, here the basic car chassis, and then you've got the simulation parameters here. You can turn up the scale of the noise displacement, and or make it faster or slower. And so these are the spring constants and the damping constants, and so those are the parameters for Hooke's law and the proportional damping. And so these are just some values that I picked. The one set is for the chassis links, and the other is for the suspension. So I can set it up to color each of the links based on the whether the state of the tension, whether it's in tension or compression, and they're just kind of rotational type of things. So it's nothing fancy right now, but it's kind of just showing off this type of a system here.